Hello everyone. So I'm here to talk about a project that I've been working on, a few other people too, called Peer Maps, which is peer-to-peer cartography. So that's the website, peermaps.org. That's me. That's my co-op. We work, yeah. Okay, so I've been doing this stuff for a while. Here's some of the previous projects and kind of how they relate. This was alluded to a little bit earlier with Carissa and Nafel talking about the work with Mapeo. It's also something I've worked on. I've also worked on the OSM P2P stack for doing offline mapping. And what Peer Maps is it's bringing a lot of these ideas and these techniques to the whole OpenStreetMap as a replacement for Google Maps or hosted centralized mapping services. I've been doing this actually for a long time. This is a slow-burning Omega project, as Dominic likes to call them, of work. Actually, my second job was at university working in GIS for like about a year. So I kind of got learned some things like Proj 4 strings and other stuff. I've also been kind of around adjacent to peer-to-peer tech for a long time, doing work early on with the early DAT stack and Hyperlog and things. Luckily, with Peer Maps, we recently got the Samsung Stack Zero grant for building this thing. So just a little bit more, it's already been covered today, but OSM P2P and Kappa OSM are the databases behind Mapeo, which is for very offline-centric use cases. So this takes the OSM, the OpenStreetMap data model of nodes, ways, and relations, and it puts them into a peer-to-peer database where you can sync like with USB drives or with whatever network is available. First version was on Hyperlog, and now everything is on Hypercore with Kappa Core, which I'll also talk a little bit about more. Mapeo gives you this peer-to-peer sync with a mobile editor, and the whole project of Peer Maps is about kind of creating basically a web experience for maps. Of course, you can build a lot later, but that's sort of the initial direction for this. So you can put a map embedded in a website. It's really difficult to do that right now, actually. If you've ever tried it, you often have to put in your payment information before you can do anything. And they sometimes change the API on you also. I remember an old project I had with Google Maps. They like deprecated that API, and then my thing just broke. And then, well, can't do anything until you fix it. So this is kind of part of my motivation for the whole thing. So Peer Maps has a lot of pieces for this early version of making a Google Maps replacement. A big one, the riskiest one, I'm going to demo in just a little bit, is called Evros. That's the Y sound is a V. My friends in Greece told me that means interval in Greek. So it's a database based on interval trees and Bkt trees, and we'll talk about that a little bit. The next part is a cooperative computing cluster like SETI at home, which I hope to use for doing the batch processing, and I'll show a little demo of that, and then the rendering stack. So that's building tiles, well, not building tiles necessarily, but just drawing the database results in a way that maps well to how the graphics card expects data to be passed in through attributes into shaders. I'd like to preserve a lot of the nice things that I've been doing with my prior work on Mapeo, with OSM P2P, building offline capable tools and sort of taking that on as an early goal into the project, but also making something that can really last, where even after I'm moved on from this project, other people can kind of take up the mantle. And I've got some more ideas on how that would work. So for editing, you can use this thing, Kappa architecture, which people have talked a lot today about. That's where you have an append-only log, and you build materialized views, which is a fancy word for index, on top of them. Some open questions that I'm starting to run into a lot of these myself is, how do you handle sparse data? How do you maybe transmit some of the views that you've sent to other peers? And this is, I think, something that we should be thinking about if we're building these really massively scalable systems and actual alternatives. So this distinction between like sparse, so you can generate views from an append-only log pretty easily on one system, but you run into trouble when you have a data set that doesn't fit on one computer anymore, or that you, for reasons, can't send over the network. So with Peer Maps, it's going to distribute pre-computed Planet OSM view. That's the whole Planet OSM data model that you can download from OpenStreetMap. The protobuf file on that is like 40 plus gigabytes, so it's not too big, but it's not necessarily a trivial size of data. And the other goal is to eventually provide an editor on using these techniques with the Kappa architecture, having a append-only log where you can materialize a view as like kind of a layer like you might see in traditional GIS tools. So the first piece that I want to talk about is Evros, which is this multi-dimensional spatial database. So I've built several of these spatial databases now. Some of the earlier ones didn't really even work, but I think I've gotten kind of good at it. These two on the screen have been used in deployment situations, and I think they worked okay. I mean, the KDB one was a bit slow, but then I made a fast one that I think is much better in actual situations, can scale up to at least a few million nodes, not without too much trouble. And this Bkt tree module is also the one that's currently being used in Mapeo. And eventually, I think the plan is to switch over that piece to use Evros as well. So let's first just talk a little bit about spatial data and trees, because it's sort of relevant. So you might have seen a binary tree. This is a data structure where you have a left side and a right side. And based on what that number is, I call it the pivot point. I'm sure there's some other name for it, but based on what that number is, you either go to the left if the data that you're looking for is less, or you go to the right if that key is greater. And you descend down these levels. There's a really cool trick you can do if you want this to be multidimensional data. So this is two-dimensional by nature. If you want it to be multidimensional, this is the trick. So every level of the tree in this data structure called the KD tree, you just alternate what dimension you look for. So the first level, level 0, you might treat that as the x coordinate. And then the second level, level 1, you treat that as the y coordinate. And then maybe if you have 2 dimensions, you go back to x and then y and then x and y. Or if you have 3 dimensions, you go x, y, z, x, y, z, x, y, z. And so you run out of levels. Another fun idea here is a B tree. So B trees are really great because usually with binary trees, the branching is only 2, so you have a left side and a right side. So it takes kind of a lot of hops in practice to get to where you want to go. So B tree is a way to sort of short circuit that process by packing more child nodes into each level of the tree. So this is the diagram on Wikipedia for B tree that I converted into ASCII here. This also has a branch factor of 5, so you could fit 4 values into each level of this B tree, but you have 5 child nodes because you have one on the leftmost and then the rightmost. So you have +1 in the number of nodes. Anyways, so there's a really cool paper that I like a lot that describes this kind of tree called a Bkt tree that combines what I just showed about B trees with this idea about KD trees. And it also brings in another invention that is an LSM technique called forest of trees in that paper, which I think is quite good. I mean, it's working pretty well in practice here. So what are LSM trees? I know I'm going somewhere with this, I promise. So bear with me here. The Bkt approach uses this. I think it's really cool. So you start out with a staging value. That's like data that would fit in memory. And then you go to the first tree, and that's size b, or b times 1. And then you go to the next tree, which is whatever that size was times 2, and then times 2, and times 2, and times 2. And what this lets you do, and then each tree can also be empty or full. If it's empty, then, anyways, this is how it works. What's really cool about this technique is it sort of mimics how binary counting works. So if you have full trees, that's sort of like 1, 1, 1. So in this example, we have a staging of size 1, or b. And then we have the first tree, which is size 1. Second tree, which is size 2. And then the next one is 4. So 1 plus 2 plus 4 plus 1 always equals the next power. So you can basically traverse, so long as you have full nodes, and stuff all of that data plus the staging size into the next empty bucket. That's the basic technique of that paper. I think it's really cool, and everybody should know about it if you care. So here's some math that is actually extremely trivial math, but I'm just not even going to talk about what that means, but it's basically what I just said. So you can do better than this also if you have staging size that is greater. Like if you have more data that you want to write at once, you can pack that more efficiently into these data structures. So you create a mapping of, in binary, the size of all of the staging data that's about to be written in one batch in powers of 2, and you can map that directly into the vacant and occupied trees in this sort of growing forest of trees. And that's an example of this. So this is some Rust code that shows how, like the operations that are being planned that you can do. Yet another tree, and I promise I'm going somewhere with this, is an interval tree. So this is a really cool data structure. It's just like the binary tree that we already saw, but instead of storing points that might be, a single number, you can store intervals which have a lower bound and an upper bound. And if an interval completely is off to the left and it doesn't intersect, it goes to the left tree. If it's completely off to the right, it goes to the right tree. But if the interval intersects that pivot point, then you make a pointer and you jump somewhere else into another structure, and then you can repeat recursively this sort of thing. So that's the basic idea. And what Evros does is it just combines all of those techniques into one database, which happens to work really well, I think, with known techniques for peer-to-peer distribution. So it's Bkt tree based in its basic design, and then it has all of the properties of interval trees. And here's also the data page format if you care. This just shows, this is another trick you have to do to make it work in practice, which is basically each branch is another little tree. And then another important idea with this database is that you have these, when you write data, you write a bunch of data at the same time. Like you have a block size that you specify. So you might write 3,000 records at once into this data file. And the data file is append only, and it grows in size. This is really cool because it lets you have, blah. So if you write data in these really big chunks, like 3,000 at a time or whatever, if you have points, you can take all of the data that's in one block and represent that as an interval. Or if you have intervals, you can also represent all of the intervals in that block as a single interval, which is really useful for doing merges. And that's really important if you want to build a cooperative computing cluster with this geospatial data, because that amount of information is so much smaller than what you actually have in your data block. So you can keep all of the data files on the individual nodes, seed them to a peer-to-peer network, and then take just those bounding ranges of the data pages and ship that to a reducer node, and you can do this kind of MapReduce process where you generate something the scale of Planet OSM, which has 5 billion plus nodes in it. So I'm going to do a demo now with some assistance here on the microphone. OK, so this is the Evros data. This is the Evros code. It's written in Rust. So I have some examples I want to get through really quick here. I have a grow example. So all that this database does is it has a query method and it has a batch method. Query takes a bounding box, and batch takes an array of values that you want to stuff into this database. So in this example, we stuff 10,000 records per batch, and we do that 100 times. So 100 times 10,000 is 1 million. So this example will write 1 million records, and it will print out the time that it took. So if I run this example in release mode, of course, can't forget that, and I can give it a location, so I'll call it cool. Here we go. So it wrote 1 million records in 1.4 seconds, or about 700,000 records per second. And I'll do this a few more times. I'll call this one Berlin. And I'll do it yet again. That one's called wow. Wow. Okay. Okay, so now we have, let's just go ahead and look at these, cool, Berlin, and wow. Here it creates this forest of trees, like I was demonstrating on the slides. So these trees are either full or they have data. We have the data page, which in this case is 30 megabytes. Oh, sorry, there we go. So we have this data page that's 30 megabytes. That's the append-only file. We have this range file that represents the bounding extents of each block in the data page. And what's really cool is we can then just take only these range files and run the whole interval algorithm just on those as the input points, which is really fast because if you look at that, that range file is 56 kilobytes for 30 megabytes of actual data. So this can be done like probably on a single node, or you could also do it recursively if you have a huge amount of data. So I can go ahead and run this merge example. I think it's just called merge in release mode. And then I pass in the databases, cool, Berlin, and wow. And then I think the first argument is the, okay, so that was almost instantaneous. And it created this new directory called merged. It just so happens that all the data, oh, there's a tree in there. So this merged all of that data into this, this database that just contains offsets into the other databases. So you can imagine using, for example, the new hyperdrive mounts that Matthias talked about earlier to kind of have that mapping with this peer-to-peer data. And I can run then this query command. So mquery, I believe it's called, in release mode. Don't forget that. Your program will be really slow if you don't. And then run it on the same data files. Because I have to have the original data files also to reference the actual data in there, because the other one just has pointers. And I can give it a bounding box, so I'll just print out all the data.
Merge with the D.
Was it merge? Oh, thank you. Okay. There we go. So we got some data. Well, anyways, it also has an error you can't see at the bottom. But yeah, so we just merged all of this data into another peer-to-peer database. So basically, what we can do now, thank you, is we can put all of this technology into what more or less amounts to a botnet, which is also, I feel like this used to be a more popular idea, especially in the original generation of peer-to-peer, like in the BitTorrent era. Projects like SETI at Home and protein folding and this kind of utopian vision of why can't we all just pool our resources and have a better world for everyone. Less of that these days, but I'm trying to carry the torch in my own way. So this is a project that I've been working on as part of Peer Maps called Swarmhead, which is just that. So I really think it's important that we consider using capacity on computers that have already been made, because more computers means more mining and more extraction and more sweatshop labor and just, we have enough computers. I don't think we need any more. Like, let's just use the ones that we've got, actually. And also, we can maybe just trust people even a little bit, even verify it, instead of wasting Denmark's worth of electricity. I think that's a really important thing, too. So doing more with less, I think, is really important. Like, how do we coordinate a lot of different nodes all cooperating for like these big projects? I think being able to use spare space might mean that you only use, like 2, 4, 5, 10 gigabytes on like somebody's VPS node or Raspberry Pi running somewhere. Different computers have different capabilities, and I really think it's important that we take the time and expend the care to just make use of what's already there, because there's a lot there if we can organize it. And also, computers aren't always online, and that's a good thing. And I think that also makes our networks much more resilient against cascading failures and giant planetary deserts like we saw earlier. That's pretty scary. And nodes shouldn't have to have the full archive. I think that's been proven with some other projects that that's maybe not the best idea. So there was already a project like this for OpenStreetMap called Tiles at Home. And this is really sad because it was shut down. It was running at a university somewhere. And it was shut down because someone from the IT department came by and said, oh, this computer is using way too much net bandwidth and disk and electricity. And because all of the coordinating was done on a single machine, it was vulnerable to not necessarily malice, but just, you know, somebody comes in and they can't run it anymore. And that's really sad. So how can we design systems that can, like, aren't vulnerable to a single person being in charge of it anymore? I think that's really important. Like, longevity and cooperation are kind of intertwined, and how can we also find ways of giving power to others who might want to take up the mantle, and also, like, if we are bad actors and being negligent in running these systems, or people have different ideas about how a system should be run, they should probably be able to fork it, for example. Like, this whole network should be really trivial to fork if someone wants to do their own thing, and then they convince other people to join their network instead. Also, moderation, I think, is really important. So this is kind of, you kind of need good moderation tools to have these systems at all, but what does that look like? There's a lot of different ways to do it, so I've got a module for that and some experiments. But now let's do a demo of this cooperative computing cluster. Okay, so so the first thing you have to do is you have to create a database. So you give that location for the data to live. So I'll call this A. This is just a directory in the current place. And it gives us back this key. This is a public key. And then what we can do is we can deploy a command. So I'm going to deploy with this A database a message that is a command. So I'm going to run the date command, +t dot +n, which is nanoseconds, and you know the date command. OK, so then I get a job ID. And now I can join the network. So these are all stashed. All of these messages are local on this machine. So, well, the whole demo is local, but I can run the join command, which reads in my key from a database and creates a swarm around that public key. So this is running. Now, in another node, I can run swarm. Wow, what is going on? OK, there we go. That was weird. I can run the swarm head command now as a worker. So I can join the network, and I'll give that a new database name. OK, so now it should connect. There we see the connection. And it should also run the command, which maybe it's doing, actually. And then in this other computer, I can now see what has been done. So I can sync all of the data to this other database called Z. So there we go. I've now synced all the data, and I can see what the jobs are. There's the job, and then we can see the output by going to that. Oh, and that didn't work. Well, anyways, you get the idea. So it's your basic botnet stuff. What I noticed earlier this morning is that what I really want, so this is using Capicore and multi-feed to coordinate all of the pieces. What I really want, though, is basically an IRC channel. This is what real criminal botnets actually use, and it's actually great. One time when I was in high school, I think I stumbled onto this IRC channel where someone actually had a botnet, and it was just fascinating to watch how this thing was being administered. But we already have a peer-to-peer IRC, and that is Cabal. So I'm really looking forward to integrating this kind of botnet tech with just like a chat room. That's really cool. And what's great is you can join the chat room and like see how it's run and like comment and ask questions, and you can learn, and we can all learn from each other about how to run cooperative infrastructure. I think that's a really compelling idea. OK, so the final piece here is the graphics layer. I mean, there's some more pieces, but you get the idea. So basically, I've been doing a lot of WebGL for a while now, and I wanted to design this whole project so that it was really designed so that you could run this data directly from the database and stuff it into the GPU in WebGL. So to do that, well, you need to minimize the number of draw calls, and there's a lot of customizations that I think people might want to do, like custom projections and making just weird, cool maps. I really love that kind of stuff, so I would like for this project to help support these kind of use cases. Maybe we don't need tiles, actually. If you can take the data from the database directly and pack it into buffers and pass that to the GPU, then that's it. And this interval structure is really great for this sort of use because tiles are kind of an artifact of using databases where you don't necessarily, you might have to do a bunch of polygon clipping or whatever to pack things into the appropriate format. But with an interval tree, if you have a really, really long straight highway, for example, that goes, and then you're looking at a tiny town on that very straight highway that maybe only has 2 points that are far away, that bounding box is going to just, by way of how the tree traversal works with an interval tree, you're going to get that feature anyways, so you maybe don't need tiles or this other sort of infrastructure. We'll probably have that eventually also because there's a lot of legacy tools that might want the peer-to-peer parts of the project, but it's just nice to think about like what we can discard and what we can take from the future tech. So these are the basic types of points that you might need to do rendering directly on the format. And we've got a basic draft spec here that my colleague Marina put together. And here's an old example. So this is a neighborhood where I live. I'm not going to show you exactly where. That'd be weird. Unfortunately, this map is kind of old because there was an eruption that happened. But yeah, so this is pretty cool. This is like an 8 megabyte tile that's being rendered all at once, like in just a few draw calls. One of the really hard pieces, though, of getting this tech to work is not actually all the peer-to-peer stuff. That's fairly straightforward. It's just you have to put in the effort. It's label placement. You have to put the like text labels on, and they have to like look nice. And that's just really hard to do. So that's one of the big challenges, is making things look nice and just make something that people want to use. That's very challenging stuff. So that's all I have. Thanks.